Hello everyone, welcome back. This is our polymer reaction, or polymers reaction pre-lab lecture for Organic 1 CH4511. So in this experiment, there are going to be 4 different polymers that are created. And so just kind of talking about some of the things here for polymers. We have 2 main approaches for polymerization. We have chain growth, which can fall under which could have a cation intermediate, an anion intermediate, or a free radical intermediate. And we're mostly familiar from the lecture side of things with free radical intermediates, where you have those 3 steps: initiation, propagation, termination. But you can have cations and anion intermediates as well. And a lot of times, what you see with this chain growth, it's the same. It's just a bunch of different molecules of one given monomer, and they just attach with one another. So you see a lot of repeating of the same thing, right? So in this case, this 2 carbon chain just keeps repeating, right? And so that's why you see the parentheses just around the 2 carbons. Now, also you have what's called step growth or condensation polymerization, and the reaction of nylon 610 is a good example of that, where you actually have 2 different molecules coming together. Um, and this actually follows a carbonyl-based reaction that you talk about quite heavily in Orgo 2. But upon that polymerization, you see that you can have this repeat. You notice how you have this molecule has an amine on either end, while this molecule has an acid chloride on either end. And so, it's in essence, you're having an amine acid chloride reaction happening. And I'm going to show an example of that in a second, um, to where you know this nitrogen reacts with that carbonyl carbon, and that's why you see that bond being formed. And then you notice you get another amine on one end that can react with another end of this, and so that's how it can just keep going. Also, something else to think about is also what's called cross-link polymerization. You're going to be doing an example of that cross-link polymerization um, when you are using sodium borohydride. Um, and so a lot of times what this does is it adds more rigidity, or it makes the polymer stronger, or more stable. For instance, the molecular weight of a cross-linked polymer can be quite huge. For example, tires. Uh, Tires are an example of a cross-linked polymer, and the tires are exceptionally stable, right? If they weren't, we wouldn't want to use them on tires. We wouldn't want to use that rubber that's made in tires on our cars. All right, and so because they can withstand very hot temperatures, very cold temperatures, and still maintain a lot of integrity. All right, and then there's a lot of ways that we evaluate polymers. A lot of ways that we can't necessarily do it because we don't have the instrumentation in lab, but you can look at the tensile strength, the glass transition temperature. I mean, that's if the polymer you're making is glass. Elongation and tear resistance. All of these are things that you can look at, or type physical properties that you could evaluate. With that being said, the 4 different polymerization reactions you're looking at, you're going to create nylon 610. That one's pretty cool looking. You're also going to create slime from polyvinyl alcohol, and that can look pretty gross. Then you're going to be having 2 different polymer ball based experiments, where you can either have the polymer ball, or what you could also consider silly putty, where you use Elmer's glue. Um, but with that being said, kind of coming back over here and talking about things. Polymers. What is a polymer? Well, if you break apart so polymer into its 2 uh, original Greek meanings. Poly from polis means many. Meros means part, so many parts, right? A bunch of monomers come together. And so when we talked about this step growth, especially with the nylon 610, there's a lot that's going on here, and I'm trying to show you the mechanism as simply as possible. You'd actually kind of show this as 3 independent steps. I'm showing 3 steps in one, so the arrows do get a little hectic. But a lot of times what you see here is the nitrogen of the amine is going to act like a nucleophile, and that lone pair is going to attack the partial positive carbon of the carbonyl, and then it's going to flex that pi bond up, and then in the next step, you'll see it push back down and then kick off the chlorine, and you'll get Cl minus, and that Cl minus can actually help take one of those hydrogens away. So that's why you see electrons attacking one of these hydrogens, and then you can break that NH bond. And so that's why here you only have one hydrogen, but you have formed this nitrogen carbon bond. All right, so you have kind of this amide functionality that's been made. All right. Now, also with this, um, in terms of chain growth, like you have seen this before, especially within the Orgo 1 scope. For chain growth, when we look at radicalization, radical polymerization here, if you look at a simple alkene like this one, we've talked about how you can go from this monomer forming a polymer that has all of this. And you notice that really it's the pi bonds that help the addition process continue, the addition steps continue, so that's why you no longer have a pi bond here, it turns into a single bond, but it is radicalization, so you have three steps. You have an initiation step. Typically we see that happening with a peroxide, an organic peroxide of some kind, so in the presence of heat you do create these peroxy radicals, and then under the propagation steps here, your peroxy radical will react with a non-radical alkene, and you'll see that you'll add that OR to the structure, and now your radical is the other carbon, right? So the oxygen adds to this carbon, so that's the one that becomes the radical, and then this becomes a reactant for another propagation where it reacts with another non-radical alkene. All right, and so in essence, you could just keep seeing this radical would now react with another one of these, making, right, a longer chain, and so that's how you have that chain growth occurring there. Okay, I'm not really showing the termination, but you do need to get in the habit of seeing a termination, right? You have a radical plus another radical, and they produce a non-radical. Okay, so that's very good to remember. Okay, for your termination step. All right, and then finishing up, since we are actually doing a cross-linking reaction, I'm talking about how tires, we can see this with the formation of rubber for tires. So in a cross-linking polymerization reaction, what it is you have your original monomer will actually have a third site for reaction. So the first two sites help make this type of polymer, right? And so you see you have this alkene still present in the polymer. And what this will do is this becomes our third site that could react with sulfur, so S8 here. And in the process, what happens, it actually links multiple polymers together, like this polymer, right? It links multiple ones of those together with this disulfide bridge. Okay, and so what this does, when you look at this, it actually makes it more stable, because what can wind up happening with these is that they could become all tangled. Like imagine that you have, like, each one of my fingers is the polymer, right? So what can happen is these guys have a whole lot of single bonds in there, so they can become all knotted up, right? And pretty much get all tangled up, and they're not very stable when they're tangled up. But when you create these bridges here, it's like, okay, so you've added a line and a line with a bridge in the middle, and so now there's only so far that they can bend with respect to one another, right? So they won't get tangled up, and that makes them more stable. So cross-linking is great for that. All right, so with that, you should be prepared to take your pre-lab quiz, um, as long as you have tried to also read the manual.